Hi everyone, welcome back. Today we are going to understand a very important topic from electromagnetic waves, which talks about the momentum. It talks about the momentum density. So basically, when electromagnetic wave, this is an electromagnetic wave, which is propagating in the z direction. Okay, z cap is propagation direction, and when this electromagnetic wave travels in the space or through any medium, it carries energy per unit volume. We know that. And actually, we did a whole video on the energy density. So it carries energy density. Energy density means it carries some energy per unit volume. So basically, if we take some volume in the space, like unit volume, let's assume this is a unit volume, we take, and if we try to see how much energy is stored in this volume, in an electromagnetic wave, how much is the energy present in that volume, we call that as the energy density, so energy per unit volume. And obviously, that energy is present in the form of electric field and the magnetic field. So we did a whole discussion on that thing in the last video, but today we're going to understand that in addition to the energy density, that is energy per unit volume, this electromagnetic wave has a momentum density. That means it carries momentum with it. Okay, so it carries momentum. So basically, now we have momentum density. What is the proof for that? So basically, when this electromagnetic wave strikes any of the surface, okay, so basically it puts a pressure on that surface. When the electromagnetic wave strikes any surface, so that surface feels the pressure of that electromagnetic wave, and that's because the electromagnetic wave carries a momentum. Okay, because that carries a momentum density. That means momentum, it carries momentum per unit volume. So take if we again take a unit volume, okay, how much momentum is present in that unit volume, we call that as the momentum density. Okay, and how do we know that it carries a momentum in addition to the energy? So actually, when the light or the electromagnetic wave hits a mirror and gets reflected, so it actually exerts a pressure on the mirror, or it exerts a force on that surface. Okay, and the only logic behind is that this electromagnetic wave actually has a momentum per unit volume. And actually, momentum also gets changed in direction when it strikes the mirror. Okay, this is sort of some mechanical effect. Okay, which we see in physics. So again, there are certain notations that we use. One is g. Some books use g for the momentum density, or some use a different notation like pd. This is the momentum density, and it is actually the Poynting vector divided by c square. This is the basic definition. Let me go with the g actually. So this is actually the momentum density as a Poynting vector by c square. This is the basic definition of momentum density, and where s is the Poynting vector. And I don't need to tell now what is the Poynting vector, because I also did a whole lot of discussion on the Poynting vector. But let me tell you, Poynting vector tells us, you know energy per unit area, per unit area, per unit time, passing through the surface. Passing through surface. So basically, if we put a surface here, some sort of surface, in the unit time, in the unit time, that is, let's assume 1 second, and through the surface area of 1 centimeter square, how much energy actually passes through the surface in unit time? That tells us about the Poynting vector, and we know Poynting vector is actually 1 over mu 0 E cross of B, or like we can write it as E cross of H. Okay, this is the basic definition of the Poynting vector. And now, since this Poynting vector has E cross of B, and we know for electric field, for this electromagnetic wave which is propagating along the z direction, so this axis as a z axis, okay, is given by the E naught, okay, cos of kz minus omega t plus delta. And since polarization is along the x-axis, that is in the direction electric field is varying, so x cap is the direction of polarization, and B is given by B naught cos of kz minus omega t plus delta y cap, because now there only remains one direction, which is y cap, in which the direction magnetic field would be varying, because electric field and the magnetic field would be perpendicular to each other, and it must be perpendicular to the direction of the propagation. So z cap is the direction of the propagation. And since E and B contains in it cos term, okay, if we do a cross product of E cross B, what we get, so we get S equals 1 over mu 0. It would give us E naught B naught cos square of kz minus omega t plus delta z cap as a whole vector. So but we know B naught is E naught by C, so it would be E naught by C by mu 0 and cos square kz minus omega t plus delta. Let me write it as the magnitude of S, and it becomes E naught square by C mu 0. We can actually replace mu 0, okay, from using the speed of light concept. C square is 1 over mu 0 epsilon 0, so 1 over mu 0 is epsilon 0 c square. Let's put it here, which is actually mod of the Poynting vector is E naught square by C, and 1 over mu 0 epsilon 0 c square cos square kz minus omega t plus delta. So cc will go, so it would give us C times epsilon 0 E naught square and cos square kz minus omega t plus delta. So basically what I mean is that this Poynting vector contains in it cos square term, and we know cos square is actually sinusoidal in nature, so we cannot talk about the absolute value of the momentum density, but we should talk about the average value of this momentum density. That is why we take sometimes the average of this average of average of the momentum density as average of the Poynting vector by C square. And since if we take the average of the Poynting vector here, C would be there, epsilon naught would be there, E naught square would be there, and cos square average would be 1 by 2. So that would be a Poynting vector average, so 1 by 2, so it would give us 1 by 2 C epsilon naught E naught square. This is very important formula. So basically this average of the Poynting vector is 1 by 2 C epsilon 0 E naught square by C square. Okay, CC gets cancelled, so there remains 1 by 2 epsilon naught E naught square. Let me take 1 by C outside, and this is the average of the momentum density, and 1 by C, if you know this thing, this is actually average of energy density. The energy density I wrote here, this energy density, okay, actually this is actually average energy density U. If you haven't seen the video, I have proved that how average of the energy density is 1 by 2 epsilon naught E naught square. Okay, I can do it in a minute how average density, average energy density is this. Okay, we can do it in a minute. Actually energy density, not average, energy density is given by 1 by 2 epsilon naught E square plus 1 by 2 mu 0 B square. And this is simply energy density formula, energy density, not average. Okay, this is energy density. And we can put electric field here, we can put electric field here as this, and magnetic field here as this. Okay, I'm proving that how average energy density is given by this formula. Okay, I'm going to prove it again. I did it in the last two videos, but if you haven't seen that video, okay, there is no need to go back, just have a look on this. Is very simple. So this is the energy density, that is energy per unit volume of electromagnetic wave, which is present there in the form of the electric field. This part contributes that thing, and in the form of the magnetic field, this part contributes that thing. And we can put that electric field value here and the magnetic field value here. Let's put it, let's see what will happen. 1 by 2 epsilon naught e, in place of the e square, we'll put e naught square and cos square, and let's write it some x. Okay, and we know x is this whole thing. Okay, let's write some theta, okay, in place of this whole thing as a theta, and plus 1 by 2 mu 0 in place of the b, we will write b naught square, and it's again cos square theta. Okay, so this is energy density. Now if we try to calculate average of the energy density, so 1 by 2 epsilon naught e naught square, and average of this thing would be 1 by 2 plus 1 by 2 mu 0 b naught square, it's would be 1 by 2. So it would be 1 by 4 epsilon naught e naught square, 1 by 2 1 by 2 1 by 4, okay, 1 by 4 mu 0 b naught square, because average of the cos square is 1 by 2. Okay, and there is again if we'll manipulate this thing a bit, we'll get this thing. Okay, let's check it. 1 by 4 epsilon naught e naught square plus 1 by 4 in place of 1 by mu 0, it's 1 by mu 0 here. In place of 1 by mu 0, let's put epsilon naught c square. Okay, let's put epsilon naught c square. Am I correct? And in place of b naught is actually e naught by c, and it's b naught square, so b naught square is e naught square by c square. So it's like e naught square by c square, c square will go, so it's 1 by 4 epsilon naught e naught square plus 1 by 4 epsilon naught e naught square. So that will give us 2 times, that is 1 by 2 epsilon naught e naught square, and this is actually average of the energy density. That is why I wrote here 1 by 2 epsilon naught e naught square as average of the energy density. So basically the momentum density is 1 by c times average energy density. Okay, or we can write the average of the momentum density is average energy density by c. So final conclusion would be average of momentum density is average of energy density by c. I proved it for you. So basically this formula you should remember, and in place of average of energy density you should remember 1 by 2 epsilon naught e naught square. Okay, I hope you understand this whole concept. I tried to prove every statement, but this is the basic definition. Momentum density is given by Poynting vector by c square. This definition you have to remember. This is actually the basic definition, and I hope you get the idea of what is momentum density stored in the field. So basically, in addition to the energy per unit volume carried by the electromagnetic wave, it also carries the momentum per unit volume, which we call as the momentum density. And that momentum density is given by the Poynting vector by c square. And since that Poynting vector itself contains cos square, so we must take average into consideration. That is why we take average of the momentum density as the average of the Poynting vector by c square. This definition is also correct. And if we expand it a bit using the definition of the Poynting vector, which represents energy per unit area per unit time passing through the surface. If you have confusion in these like terms, what is energy density, what is energy flux density, what is average energy density, what is intensity. All these terms have been explained by me in the probably video number 6. If you check my lecture 6 on the playlist of electrodynamics, you can see there all these terms have been explained, and all these things have been explained in very details there. And I hopefully you get the idea of what is momentum density in this video. Thank you so much.